All right, I think we can start. It's 12:15. Welcome today to the lecture on empirical economics. We are happy to have you here again. And if there are any questions, let's start with that. If there are any questions concerning what we did last week, don't hesitate and just ask or write us a chat. Okay. Otherwise, we start right away where we stopped last week. Let's go just one or two slides back to see where we stopped. We've seen that in the multivariate linear regression model, the outcome, the estimator, is a random variable. So the slope coefficient that we estimate from the data is the random variable because it's estimated from the data. The data themselves are considered as random objects. So if we compute the estimator from the data, and if the data are random, then of course the estimator is also random. And we derived, we didn't really derive that. You can do that in the elective courses on econometrics. But we stated the result that the asymptotic or approximate distribution of this estimators, the slope coefficients, is a normal distribution. So the asymptotic distribution, say, of the first slope coefficient is a normal distribution, and it's centered around the true value of the slope coefficient. So of course the estimator is not always equal to the true value. Sometimes it's too large, sometimes it's too small, but it's centered around the true value. And also we can derive the variance of the estimator, which is a measure of the precision. If the variance of the estimator is small, that means that we vary only a little around the true value. But if the variance is large, then of course our estimator can be widely too small or too large. So the variance is also interesting. And of course, the same can be stated for all other slope coefficients as well. So we don't only have beta 1 hat as a normal distribution with this expectation and this variance. We have the same results for all the other beta coefficients, for all the other slope coefficients, and by the way, also for the intercept, in which we are normally not that much interested. All right. Of course, the variance of this normal distribution has to be estimated as well, but that can be done using the data we also use for the estimation itself. And then we can derive this so-called standard error of our estimator. So we denote that, or most textbooks denote that by SE for standard error. And the standard error for the slope coefficient is the square root of the estimated variance of our estimator. Okay, and again, it's to be considered as a measure of precision of our estimation. Then one can show, or it's relatively easy to see, that if we standardize our estimator, that is, if we subtract its expectation, beta 1, and if we divide this difference by the standard error, what we get is a standard normal distribution. And that's a very comfortable result because we know how to deal with standard normal distributions. Okay, so this is our starting point for today. So we have seen that the standardized version of our estimator has a standard normal distribution, at least approximately, which means that if our sample is large, say a few hundred observations, most of the time we actually do have large samples, a few thousand observations, and then this approximation is really excellent. And since this is exactly the same outcome as the one we have derived in the simple linear regression model with a single regressor, we can perform a t-test exactly in the same way as we learned in the simple linear regression model with a single regressor. Okay? So there's nothing new here. The only difference is that we can not only do that for the first slope coefficient, beta 1, but we can do that for any of the slope coefficients and for the intercept term as well. So there's nothing really new. Concerning confidence intervals, there's also nothing really new. We construct confidence intervals for the slope coefficient exactly in the same way as we learned in this simple linear regression model with a single regressor. So we take the point estimate, beta 1 hat, and we add and subtract roughly 2 times the standard error. This 1.96 is the quantile of the normal distribution that has the property that the resulting confidence interval covers 95%, with 95% the true value. Okay. So in this case, that's the most typical value we use here. As I stated in the single regressor case, a good rule of thumb is just take 2 times the standard error, subtract that, and add that to the point estimate, and then you get roughly a 95% confidence interval. And of course, if you substitute beta 2 for beta 1 hat and the standard error of beta 2 hat for the standard error of beta 1 hat, then you get a confidence interval for the second slope coefficient, and so on for the other slope coefficients. So that's exactly what we learned in the week before. So let's, even though it's exactly the same, let's apply that to our running example. We look again at class sizes and test scores in California. You might remember from last week that if we include 2 regressors, the class size STR and the percentage of English learners, then we get this outcome here. So the intercept term is 686 with a standard error of roughly 9. The slope coefficient for the class size decreases from the case that we had in the single regressor model to 1.1 with a standard error of 0.43. And the new slope coefficient belonging to the percentage of English learners is minus 0.65 with a standard error of 0.031. All right, so if we want to perform a t-test in this expanded model with 2 regressors, then it might be interesting for us to look at the null hypothesis that the class size has no effect on the learning outcome. So that's the same t-test that we already performed in the single regressor case. So we would like to test the null hypothesis that the slope coefficient for class size, beta 1, is 0, which means there's no effect of class size on the learning outcome. And if we reject this null hypothesis, that would be a corroboration for the alternative hypothesis that there is, in fact, an impact of class size on the learning outcome. So it's an interesting null hypothesis. Well, the t-test is computed, as we already know, by using the point estimator, the point estimate, subtracting the hypothetical value and dividing the difference by the standard error. So we take the point estimate, which is minus 1.1. We subtract the null hypothesis value, which is 0. So it's still minus 1.1. And we divide that by the standard error. The standard error is 0.43. So we then compute the t-value, or the t-statistic, which is in this case minus 2.56, and we compare that to the critical value. And as you remember, the critical value for the t-test, if we have a 5% level, is 1.96, the same value that we use to construct 95% confidence intervals. So 1.96 in absolute value is smaller than the t-statistic, so the null hypothesis is rejected in this case. So minus 2.56 is larger in absolute value than the critical value, 1.96. So the null hypothesis is rejected, and that would state that there is, in fact, an effect of class size on learning outcomes. So the result is, or the outcome of the test is, the test decision is actually the same as the one in the single regressor case. Now let's look at the case where we would like to construct a confidence interval. So same outcome. This is exactly the same line as before, but now we would like to get a confidence interval for the slope coefficient of the regressor percentage of English learners. So remember, this is the share of students that do not speak English as a native language. And we construct the confidence interval by using the point estimate, which is minus 0.65. And then we subtract and add roughly 2 times 1.96 times the standard error. So let's start with this rule of thumb. We take minus 0.65. The standard error is roughly 0.03 times 2 is roughly 0.06. So if we subtract 0.06 from 0.65, we get 0.59. Well, it's minus, so it's minus 0.71. And if we add that, we get minus 0.59. So that's the rule of thumb confidence interval. And if we use the correct values, so 1.96 rather than 2, and not 0.03, but 0.031 here and here, then if we round that to 2 digits, we get the same result as the rule of thumb. So that would be the 95% confidence interval for the slope coefficient of the second regressor. Okay, so nothing new here. We can perform t-tests exactly in the same way as before, take the point estimate, subtract the hypothetical value, divide that by the standard error of our estimator, and then use the critical value if we have a 95% level of 1.96. And if we want to construct a confidence interval, we proceed exactly in the same way as before. We take the point estimate, we add and we subtract 1.96 times the standard error. And that's the confidence interval. And if we want to have a 99% confidence interval, we would have to adjust the quantile value 1.96 to 2 point something. Okay. All right, but we are now in a different situation. We have more than one regressor, so we can actually investigate more complex hypotheses. And that's interesting because we can more complex situations. So this is our next topic. It's called the joint hypothesis tests. Suppose we add a third regressor to our model, the expenditures per student in that district. Then our model would be expanded. We would have the intercept as the first regressor. We would have class size as the regressor that we already had. We would add a new regressor here for the expenditure per student, and also, which is now our third regressor, the percentage of English learners here. Of course, you could swap these here. All right, so an interesting hypothesis in this setting would be to check whether the learning outcome actually depends on variables that policymakers can influence, like the class size, or if the learning outcome is more related to variables that the policymaker, or at least the education policymakers, cannot really influence, like the expenditures per student that, of course we can also influence the expenditures per student. So this is also in the realm of the education policy. So these two are variables that can be influenced by the education policy. So these are interesting from a policymaker's perspective. While the third regressor here, the percentage of English learners, cannot really be influenced by the policymakers. Yeah, that's just something which is exogenously given, at least from the point of view of an education policy person. Okay, so we have two regressors which, well, describe the school situation, and one regressor that, well, describes the environment. Okay, so it would then be an interesting null hypothesis to state that the school situation actually does not have an effect on the learning outcome. Because in that case, if we can reject the null hypothesis, we can see that educational policy does have an influence. Okay? So that's an interesting null hypothesis. It's really relevant. And we can state that by saying that neither the first regressor, class size, nor the second regressor, the expenditures, has any influence on the learning outcome. Okay, so in that case, we would say that the slope coefficient of class size is 0, and at the same time, the slope coefficient for the expenditure is also 0. That's an interesting null hypothesis, because if we can reject that, then we would see that the school situation, which can be influenced by policy, has an impact on the learning outcome. What is the alternative hypothesis? Well, in this case, the opposite of the null hypothesis is obviously that either the first coefficient is not equal to 0, or the second one is not equal to 0, or both, of course. Okay, so it's not an exclusive or here, it's inclusive. How could we test that? Well, first of all, we call that joint hypothesis because we have, in effect, our null hypothesis has two sub-hypotheses. The first one says that the first slope coefficient is 0, and the second one says that the second slope coefficient is 0. That's called, therefore, joint hypothesis. And we need a joint hypothesis test if we have two or even more coefficients. So in that case, more than a single restriction is tested. So we have two restrictions here. First coefficient is 0, second coefficient is also 0. How could we proceed in this case? Well, the first common sense approach would be to reject the joint null hypothesis if we reject at least one of the two t-tests. So we could perform a t-test for the first slope coefficient, and if we reject that, then we reject the joint hypothesis. And we can also perform a t-test for the second coefficient, and if we reject either of them, then we would reject the overall joint hypothesis. That could be done, but it's wrong. So this approach should not be followed. And the reason is, it doesn't work. We put that in red here. And the reason is that this approach does not keep the significance level. What does that mean? Well, remember that we have two kinds of error probabilities. The error probability of the first kind says that, or is the probability that the null hypothesis is rejected, even though it's true. And that's really an evil mistake, because we reject the null hypothesis that is true. So if we actually commit an error of this first kind, we make a grave error, and we should try to avoid that. And we try to avoid that by setting a significance level, which is in effect the maximal level that we are willing to accept as the error probability of the first kind. So the actual probability of rejecting a true null hypothesis must not be larger than the significance level that we set. Okay, so usually 5%. But if we perform two t-tests, then the probability that we reject the null hypothesis, even though it's true, is larger than 5%. Why is that? Well, the probability that the first t-test rejects the null hypothesis is 5%. And then the second could also, in a way, on top of that, reject the null hypothesis. So overall, the probability that the joint null hypothesis is rejected is larger than 5%. But we proceed in a way that we think it's only 5%, which means that if the null hypothesis is then rejected, we think that's a very unlikely event if the null hypothesis is true, and therefore it's probably wrong. So this is our line of reasoning, and it really hinges on the fact that the error probability is as small as we set it in the significance, with the significance level, right? Okay, so performing many t-tests to test a joint hypothesis is not a good idea, at least not in the naive way that I've just suggested. So don't perform many t-tests if you have a joint hypothesis, or at least not in the way that you do for a single hypothesis. In fact, there are two solutions to this problem. The first one is we could adjust the critical value. That's called the Bonferroni method. And we don't follow that here. Just as a brief note, if you increase the critical value, then you would decrease the error probability of the first kind of each individual t-test. And you can increase the critical value such that the joint probability of any of the t-tests rejecting the null hypothesis is exactly 5%. So that could, at most 5%, that could be done. That's the so-called Bonferroni method. But there's an even better way to test joint hypotheses, and that's based on a different test statistic. So we just abandon the t-test and we use a different test statistic, and that's internationally called the f-test. How does that work? Well, the f-test is a simultaneous test of all the restrictions of the null hypothesis at the same time. And since it's a rather complex composition of, well, rather complex derivation for the f-test statistic, and since we don't really do that in the full generality here, we only look at one special case. So let's suppose that we have actually two restrictions in our joint hypothesis. Let's say that the first coefficient has a certain value, for instance 0, and the second coefficient also has a certain value, also 0, for example. Then we can compute the f statistic if we use the t statistics and merge them in this complex way. So we take the square of the first t statistic, we add the square of the second t statistic, we subtract something, and we divide by something, and then we take the half of the entire quantity here. And this something here and here is based on the estimated correlation between the two test statistics. However, that is derived. Okay, that's not really relevant here. And then in a way, we merge the two t-tests into a more comprehensive test statistic, if you like. And what happens? Well, if the first t-statistic is very large, which means probably the first part of the joint hypothesis is wrong, then the entire thing gets large. If the second t-statistic is very large, the same happens. So if one of these t-statistics is very large, then the f-statistic is also very large. And very large here means an absolute value, because we look at the squares. So if it's a very negative value or a very positive value, then the square gets very large and the f-statistic gets large. But also, if both of them are slightly large, then the sum of the two will also get large. So the f-statistic is large if either or both of sub-hypotheses are probably wrong. Okay? So therefore, we would reject the null hypothesis if the f-statistic gets too large. And then, of course, we have to be more precise what we mean by too large. But fortunately, we can do that because it's possible. We don't do that in this course, but you can learn about that in the econometrics elective course. It's possible to derive at least the approximate distribution of the f statistic if the null hypothesis is true and if we have a large sum. And then we can derive the critical values, compute the critical values for the f-test. And the critical values depend, of course, on the significance level. So usually we use 5%. Sometimes we use 1%, but you could choose any significance level, of course. Sometimes some people use 10%. But it also depends on the number of restrictions that we test. So we could actually use a single restriction, like in the t-test. We could use two restrictions, beta 1 equal to 0 and beta 2 equal to 0. But we could also use more restrictions here if we have more regressors. And the critical value then slightly goes down with the number of restrictions that we would like to test. Okay, so these are the critical values for the f-test. It's also possible to compute the p-value of the f-test. That's the probability that, well, it's again slightly complex here, and we don't derive that. It's the probability that a certain random variable is larger than the value of the f statistic that we compute from our data. And we need not really care about that, because the p-value and the test decision, if you like, of the f-test is in a standard way reported by any software packages that you use in economics. All right, so that's my part. I hand over to Andreas now, who shows you how to do that in R.
All right, thanks, Mark, and a warm welcome also from my side. By the way, we will have another active break after my session here has finished, and then after the study break, we are going back to Mr. Trede again. Let me just share you my screen in order to let you have a look at first how that works in R on the slides, and then we are going into R, and I'll code everything for you, basically what's the same thing we see on the slide, but then executed in R. We've had this additional regressor now in the regression, so the expenditure per student, which differs in some way because we don't directly need to decide on what we spend $1 for a student. So $1 or $1,000 spent on a new teacher might lead to reduction of student-teacher ratio by a certain amount here, and thus might have an effect on learning outcome. But $1 that is only recorded in expenditure per student, we don't necessarily dictate the schools how to spend that money. So we have a little distinction between these two variables in here by the way that schools are allowed to spend their money. Now let's have a look at the results of the regression when we add expenditure per student as an additional variable in our regression. And we see that again, our coefficient of student-teacher ratio vanishes or decreases in absolute value at least. Now it's only 0.28. And expenditure per student has a value of 0.0038. So at first glance, a very small value, but remember, this is the influence that a single additional dollar has spent per student per year. So a very low amount of money, obviously. On the other hand, this coefficient of student-teacher ratio decreased substantially. So we could, if we remember the last weeks, say that again in the previous regressions that we ran, student-teacher ratio obviously included an omitted variable bias due to the expenditure per student. That is correlated, of course, to student-teacher ratio, because the more money a school can spend per student, the more teachers that school could hire. So we have an influence there, and most likely we would also expect that if a school can spend more money, or if this schools in a district can spend more money on per student, then the learning outcomes might be better because the school can also buy better equipment, better computers, and better other learning opportunities for their students. So we see that there very likely has been an omitted variable bias even in the regression that contained two regressors. This now only contains our coefficients, no standard errors. In order to get them and to see them, the standard errors and the t-test, we might run the coef test command from the AER package. And remember when we talked about homo and heteroscedasticity, that especially with something like the expenditure per student, we might observe heteroscedasticity, because for very large values of expenditure, we might also expect a larger fluctuation of our residuals around the regression. So we should adjust here for heteroscedasticity, and we can do so by stating that the variance-covariance matrix should follow one version of the variance-covariance matrix function based on our regression object, and in this case, the HC1 variance-covariance matrix, which is just one version of adapting the covariance matrix for heteroscedasticity. That's not the standard way. HC1 is different from the default value in R. So if you leave out this second bracket, this inner bracket here, you would get slightly different results, because then a slightly different method for choosing the heteroscedasticity robust covariance matrix will be chosen. More importantly, what we see is that student-teacher ratio, so the coefficient of class size, gets insignificant in this regression. So we don't see anymore a significant influence of student-teacher ratio of class size on the learning outcome. But right now, it's much more important how much money a school has, or schools and school districts have on average on their disposal to spend for their students. That now has a large, or maybe not a large, but that has now a significant effect on learning outcome. And still, the effect of the fraction of English learners in our class is still A, visible, and B, very highly significant in our regression. Now, if we wanted now to test the linear restrictions that we've talked about a couple of minutes ago, namely that the coefficient of STR is equal to 0, so beta 1 is equal to 0, and the coefficient of expenditure per student is also equal to 0, we can make use of the linear hypothesis function. And that function tests any number of linear hypotheses. So for example, STR is equal to 0, a hypothesis that is linear in the student-teacher ratio coefficient. So in this case, only states the coefficient is equal to a certain constant. We can do that in R by using the linear hypothesis function. As first argument, we put in the object, in this case, our regression, that we would like to do the hypothesis test on. Then the second argument of the function is just a vector with a small c function that contains as strings our hypotheses we want to test. And these hypotheses are separated by a comma. So the first hypothesis we want to test is STR is equal to 0. The second one is expenditure per student is also equal to 0. So these two don't have a joint effect. They jointly don't have an effect. And again, we account for heteroscedasticity in our data by stating that the variance-covariance matrix is a heteroscedasticity robust one. If we run this line of code, we will get this output down here as an answer. First, R states again the hypotheses that we want to test. In this case, STR is 0 and expenditure per student is 0. And then tells us the both models. The first one is the restricted model, so the model in which these hypotheses here are true. So STR is equal to 0 and expenditure per student is equal to 0. So in this case, a model where we just leave out these two variables. And the second model is the model that we have in our object. So the full model that included student-teacher ratio and expenditure per student. And most importantly, down here, we see both our F statistics, that's 5.4 roughly, and because we are now can not only regard to single value 1.96, which we had as a 5% significance level critical value in the t-test, but because our critical value also depends on the number of restrictions we are testing, we can directly look at the p-value of that t-statistics and see that one is 0.0047. So it's smaller than 1%, and that is because the 1% critical value, the critical value for the 1% significance level for 2 restrictions, if you look it up in the table a few slides ago, was 4.61. So what we should observe here is a p-value smaller than 1%, and we do in fact so. So if you don't know the critical values by heart, or if you don't want to look up the critical values for the f-test, just always refer to the p-value, and if that p-value is smaller than either 5% or 1%, you have a significant hint that your joint hypothesis is wrong and that you should reject that hypothesis. Let's have a brief look directly how we can do that in R, or how our response when we run this code. Just ignore these first couple of lines there, just to load the data and transform the data and so on. And then we run our regression and do that just live. We run the regression with test score tilde STR plus expenditure per student plus ELPCT. And our data is from this CA school object up here. And then we have a look at our object and we get what we just saw on the slides. So just as a proof for you, the regression is just the one you saw on the slides. So STR decreases by a lot and expenditure per student now appears as an additional regressor. If we run the cof-test command, we directly get this t-test table as an output, now indicating that student-teacher ratio, so class size, is no longer an important variable in explaining what the important determinants of learning outcome are. Now let's switch to our linear hypothesis command. We have the command. And again, if you want to know anything about an unknown command, just press the F1 button while you are on with your cursor on that command. And in the bottom right corner, the help of R will pop up regarding that command. And as you can see here, the first object we need to put into linear hypothesis is the model. So is our regression object. So we just take that and put it in there. Actually. Then the second object we put in is the matrix of hypotheses, or in our case, it's just a vector of hypotheses because we have a linear model with named coefficients. So the coefficient of STR and the coefficient of expenditure per student. And these two are set equal to 0. And as I said, be careful here. You have to give these hypotheses as strings, so with apostrophes in the beginning and at the end of each of these multiple hypotheses. And then we account for our heteroscedasticity with the last line of code. And if we run this, we get the very same output as you saw on the slide. Additionally, the significance code legend is also given with the f-test or with the linear hypothesis command, and we see that 2 stars means that our significance level is between 0.1% and 1%. That's just what these 2 stars here always indicate, between which of these classical values our p-value actually is. Okay, that's on how to test multiple hypotheses or hypotheses on multiple coefficients using the linear hypothesis command, and with that, the f-test. Another interesting thought is to test whether 2 coefficients are actually equal to each other. So is the coefficient of class size equal to the coefficient of expenditure per student? So in other words,
yes,
yeah,
maybe we could make the active study break here, because that's kind of new topic.
Yeah, that might be, yeah, true. That is a good idea. So let me just switch over to the study break, which is here. You can get into position, leave your computers. I'll turn off my camera and then I'll start the video, and I need to do a new screen sharing that is optimized for video. So let me just stop screen sharing right now, stop my video, and then we can start with our active break in just a second. Okay. Yeah, I also hope that you enjoyed and that you are still present and active here. So we can continue with what we did on hypothesis testing. We've been talking about testing on different coefficients in a joint hypothesis that then contains of potentially multiple hypotheses, sub-hypotheses. Now we are going over to a little different case. That is, we test the null hypothesis that contains multiple coefficients in a single hypothesis. For example, the one that the coefficients beta 1 and beta 2 are equal to each other. In our scenario, that spending $1 per student, so expenditure per student, has the same coefficient as STR. So that reducing class size by 1 student has the same effect as increasing or reducing payment, spending $1 more on per student per year. And there are actually two approaches to test such a hypothesis of that kind. Let's first shortly go over the notation. Our null hypothesis now is that beta 1 is equal to beta 2 versus our alternative hypothesis, obviously, that they are not equal to each other. We don't state in the alternative whether one is larger than the other or something like that. They're just unequal to each other. The first way of testing such a hypothesis is to rewrite the model, so to transform our original model. Before we transform the regression model, we first transform our hypothesis, because this hypothesis, beta 1, is equal to beta 0, to beta 2, can obviously translate it in beta 1 minus beta 2 is equal to 0. We just bring the beta 2 from the right-hand side of the equation to the left-hand side by subtracting it. And then on the right-hand side, we obtain 0. And on the left-hand side, we obtain beta 1 equal minus beta 2. Then beta 1 minus beta 2, we can also rename that as a new variable. We call that gamma. And then our null hypothesis is just gamma is equal to 0. But we also already know gamma is beta 1 minus beta 2. So if we can somehow manage to get not beta 1 xi plus beta 2 x2, beta 1 x1 plus beta 2 x2 in our model, but to get gamma times x1 plus beta 2 times something in our model, so to rearrange our model in such a way, then we could run a simple t-test on gamma and test whether or not gamma is significantly different from 0. Which would be nice because that's a very simple test, a test we can even perform by hand directly and easily. So what would we need to do to our model in order to have now gamma inside the model? So we know that gamma is beta 1 minus beta 2. We have a beta 1 times x1i in the model. So in order to end up with beta 1 minus beta 2, we need minus beta 2. We need minus beta 2 xi in order to later factor it out. So we subtract beta 2 x1i, but only subtracting beta 2 x1i obviously changes our equation in total. So on the right-hand side, we would change something that we would need on the left-hand side too. So what we do is we not only subtract it, but we also add the same thing again. So we don't change the equation itself, because this change, minus beta 2 x1i plus beta 2 x1i, obviously adds up to a 0 change in total. But that might still be helpful because in this case here, we can factor out beta 1 minus beta 2 here, and beta 1 minus beta 2, we already know that is gamma. So we have already included gamma in our model. But on the right of this plus sign, we see that we now have beta 2 x1i plus beta 2 x2i. So we can here factor out beta 2 in here. We end up with beta 2 times x1i plus x2i. So nothing else than a new variable, namely a variable that consists of the sum of x1 and x2. That variable doesn't make any sense to interpret because it doesn't really make sense to sum, in our case, the student-teacher ratio and add the money spent per student. The values we receive there don't make any sense at all. But with these values, we have beta 2 as a coefficient in here. We don't need that. We are not interested in this coefficient because it's a coefficient of an not irrelevant but uninterpretable variable. But on the left-hand side, we have gamma in front of x1i. And gamma is the coefficient we only need to test in order to find out whether or not this hypothesis up here is true. So if we can reject the null hypothesis that gamma is equal to 0, then we can directly also reject this null hypothesis that beta 1 is equal to beta 2. And that is a very nice effect of this model transformation. The second method is far more easy if you know how to use the linear hypothesis test and if you have access to a computer, obviously. Nowadays, that is not a restriction at all, so we can just use the linear hypothesis. We again put in our object, our regression, where we want to test the hypothesis on, and then we just put in as a string our hypothesis. In this case, STR, so the coefficient of student-teacher ratio, is equal to the coefficient of expenditure per student. And we again adapt for heteroscedasticity. And what we get down here is, again, in the output, the student-teacher ratio, the hypothesis that these two are equal, and our F statistics, which is just 0.3638. And the p-value of that F statistics is 0.55. So we cannot at all reject the null hypothesis that spending an additional dollar has the same effect than decreasing class size or increasing class size by one student. Again, this does not state that the null hypothesis is true, but that we can only states that we cannot find severe evidence that speak against the null hypothesis. Sorry. Let's have a brief look into R, how that works in R. And here, let's have a look into both of the methods. The first method was to rearrange the model, and we needed a new variable that now contains the sum of student-teacher ratio and expenditure per student. And that's what we are doing here. We create a new variable, STR plus expenditure per student, and that is just CA school $STR, so student-teacher ratio, plus CA school $expenditure student, so the amount that is spent on average in a district per student. And then we run a second regression of test score on student-teacher ratio and student-teacher ratio plus expenditure per student and English learners percentage, because that's the variable that has also been included in our first regression up here. Now, if we run this regression, let's just click on the run button, then everything is computed. Then we can have a look at the COEF test. And not very surprisingly, we get the same p-value, 0.54673, for the test of student-teacher ratio. So in this case, student-teacher ratio is not our beta one that we test, whether it's equal to 0 or not, but it's gamma. So we have the same p-value here as we had in our slides back here. So 0.5467. Additionally, have a look at the coefficient of student-teacher ratio plus expenditure per student, that is 0.00387. And that is exactly the same as the coefficient let me just run that we have seen for expenditure per student. So the same value we obtain as a coefficient now of W, because that still is beta 2. So this one must not change. And this one here now tells us whether or not the null hypothesis that these two variables are equal is true, or if we have a significant deviation from that null hypothesis. Once we did t-tests 2 weeks ago, we also talked about confidence intervals, which we derived from t-tests, from the tests. And we can do a similar thing right now, namely we can think of confidence regions. And the question might here, what might be the confidence region, so no longer just an interval, but a whole region, an area, for beta 1 and beta 2 in our multiple linear regression model. And as the confidence interval covered the true parameters, or a single true parameter beta I, with a 95% probability through random sampling, our confidence region now should cover the parameters beta 1 and beta 2, for example, also with 95% probability through random sampling. So if we draw another set of schools and rerun all the regressions, then of course we get a different set of estimates. And we do that very often, and our confidence region now can be interpreted in a way that if we did that very often, then the region we compute as a confidence region should cover the true parameters with a 95% probability. In other words, the confidence region is the set of all combinations of beta 1, 0 and beta 2, 0, so hypothetical values for beta 1 and beta 2, that will not be rejected by a joint test, so won't be rejected by an F-test. Common sense might be to just compute a confidence interval into beta 1 direction on the x-axis and to compute a confidence interval on the beta 2 direction on the y-axis, and then we would get a nice rectangular confidence box, and all the values inside the confidence box are the values we cannot reject with a joint null hypothesis, and all the values outside that box would be the ones that we could reject. But as it doesn't work to do individual t-tests to test a joint hypothesis, this individual confidence interval construction also doesn't work when we want to set up a joint confidence interval or a confidence region. A better idea is just take a test, take the formula for the test, set a significance level, then take the critical value of that test and, so to speak, invert the formula of the test in order to get a region for all the values that we could not reject null hypotheses from. So for example, the critical value for the F-test with beta 1 is equal to some hypothetical value and beta 1, 0, and beta 2 is equal to some hypothetical value beta 2, 0. The critical value for that F-test with two restrictions is just 3.00. Very nice to learn value, just 3. Now we can take our formula. Now we can define our confidence region as the set with the curly brackets that contains all tuples of beta 1 and beta 2 values with an F statistics of beta 1 and beta 2 that is smaller than 3. So that's what this line here states. We take the set that contains all these combinations of beta 1 and beta 2 that would not be rejected by this F-test. Now, how does this set look like? Well, we already know that the F statistics was computed by the sum of the squared T statistics of the first test, the first hypothesis, and the T statistics of the second hypothesis, minus 2 times the correlation times the product of the test statistics, and so on, divided by something. If we plug in the test statistics in here, we know the test statistics for our first hypothesis is beta 1 hat minus the hypothetical value divided by the standard error, and that one squared. Then we plug in the formula for the t-statistics for the second hypothesis in here. That one is also squared. And then on the right-hand side, we have 2 times the correlation between these two times the t-statistics of the individual hypotheses. And the left-hand side here is something you might reconsider or recognize from your school math courses and maybe from the Math 101 at the university. I'm not 100% sure of that, but that here on the left-hand side is the equation for an ellipse. That part here, no, that part is the equation of an ellipse with its main axis parallel to either the x-axis or the y-axis, depending on the standard errors here, which indicate whether the ellipsis is very wide but flat, or whether the ellipsis is very high but very narrow. And the remaining part of that equation is just whether the ellipsis is turned by an angle, so whether it's upward looking or downward looking. But in the end, we can conclude that our confidence region here that we compute from inverting our test statistics is elliptical. It's not a box, it's not a triangular, it's an ellipse. And these ellipses, in the case of student-teacher ratio and expenditure per student, look like this. We have an upward facing ellipse, which resembles the correlation, the positive correlation between these two. No, are they positively? They should be. They are negatively correlated. We subtract the correlation. So, which resembles the correlation between these two parameters. The stronger the correlation, the more narrow and thinner would our confidence region be. And we see that, for example, if we only applied a box, then this box, we have this rule of thumb would go from minus 0.7 up to minus somewhere here, and this box would be somewhere in this region for the 95% confidence interval. So it would cover regions that were irrelevant for our confidence region, but it would also ignore some of the important regions of our confidence ellipse here right now. So confidence regions for for two coefficients are elliptics, are ellipses, and can be computed inverting our f-test. And you can see here, of course, an analogy to the confidence intervals we've seen 2 weeks ago, that of course, the higher we set our confidence level, so from 0.9 to 0.95 to 0.99, the larger, of course, gets our confidence ellipse here, as did our confidence intervals 2 weeks ago. Okay, that's it from my side, and I'm giving back to Mr. Treder.
I'm still here. All right. So if we consider the relationship between the t-tests and the f-test, there are kind of paradoxical results that could happen. And we would like to just show you briefly how that can happen. And to do so, let's consider a regression model with 2 exogenous variables, say x1 and x2. Then we can obviously perform 2 t-tests. We can check whether beta 1 is 0 and make a t-test, or we could perform a t-test on beta 2 equal to 0. And what could happen is, and what at first sight might seem paradoxical, is that the test of beta 1 equal to 0 and the test of beta 2 equal to 0 are both rejected. And even though both are rejected, it could happen that the f-test of the joint hypothesis is not rejected. Okay, that seems paradoxical. So the first t-test says beta 1 equal to 0 is rejected. The second one says beta 2 equal to 0 is rejected. But the f-test saying that beta 1 equal to 0 and beta 2 equal to 0 is not rejected. Or it could happen that beta 1 is not rejected if we perform a t-test on x1. Beta 2 equal to 0 is not rejected if we perform a t-test on x2. But the joint hypothesis of beta 1 equal to 0 and beta 2 equal to 0 is rejected. How can that happen? Well, let's go back to this elliptical case here. If you think of t-tests, then you would draw vertical lines on the left and on the right for class size, and horizontal lines down here and possibly up here for the expenditure coefficient. And it could happen that the ellipse is very prolonged, and it could actually be the case that well, not in this case here, but it could happen that the ellipse looks very, very long and very flat, and actually in the outer regions leaves the rectangle that is drawn by the vertical and horizontal lines. And in that case, it could happen that both single t-tests are rejected, but the joint hypothesis is not rejected. Okay? And in a similar way, it could happen that the opposite occurs. So both single tests are not rejected, but the t-test is. Okay? So in this case, of course, the question is, how should we actually interpret what we found out? But the answer is quite simple. Perform the test that you're really interested in. So if you want to perform a joint hypothesis test, then do the f-test and don't do the single, the individual t-tests. And if you're interested in a single regressor or a single coefficient, then perform a t-test. All right, so we talked a lot about including additional variables into our model. But of course, the question is, which model is the correct one? So which variables should actually be included in our model? And that's the question of model specification. And the answer, which model is the correct one, is actually quite difficult to give, because the correct choice is, well, not really defined. And many people say that model specification is more an art than a science. So it has a lot to do with understanding the substantial issue of the problem at hand. You should understand a lot about the economics and about economic theory that's going on in the model you're investigating. And there are a number of aspects that you should consider, and we are actually in the tutorials doing that all the time, model of aspects that you should consider when you think about model specification. So first important aspect is, are there omitted variables? And might omitted variable bias be a problem? Omitted variables, we've seen that 2 weeks ago or last week, are the confounding factors. So variables in the background that might have an influence on the endogenous variable and are at the same time correlated with the regressor or with the regressors in the model. If that happens, then the influence that is exerted by the omitted variable is in a way calculated into the coefficient or merged into the coefficient of those regressors that are included in the model. And therefore, these coefficients are no longer correctly estimated. So omitted variable bias is a severe problem. And if you think that there are omitted variables, then you should try to include them into your model. So the model specification aspect says that think about potential variables that might be missing. And if there are potential variables that should be included in the model, then do so. Okay. But of course, if you need an additional variable, then you need relevant variables in your data set. And sometimes these relevant variables are just not available. And in that case, of course, you just cannot merge these additional variables into your model, or add these variables to your model. For instance, if you think that an important driver of learning outcome is the quality of the teachers in that school district, then the question is, are there any relevant variables that you actually have at hand which are related to the quality of the teachers? And very often they are not. So in that case, omitted variable might be a problem, but including those omitted variables is not an option because you don't have data on them. And even if you have, then the question is, are the data you have really good enough? Is the data quality good enough? Later on, we will see that variables that are measured in an imprecise way, so if there's measurement error, then also you will get bias in your estimation. Okay? So data quality is also an issue here, which should be taken into account. But the most important point actually to remember here is think about the economic theory that's underlying the entire problem that you would like to investigate. So economic theory is really the most important part of any economic model, of any econometric model, I should say, which is actually the reason why you are learning this, well, statistical approach. You are economists, but as an economist, you must be able to do statistical analyses and do econometrics, because these two parts of empirical work are very closely interlinked. So you cannot do economics without econometrics, and you cannot do good statistical analysis without economics. So if that were the case, then you could just hire a statistician to do the empirical work for you, but that won't work because the statistician is not trained in the economic part of the problem, and therefore it will probably go wrong. That's different in other sciences, medicine, for instance. So in medicine, it might sometimes be a good idea just to outsource the statistical analysis to a statistician, because the statistician need not know much about the medical relationships that are going on underneath. Okay, so that's very important. And there are a number of points that you should try to avoid, and where you should be very careful. If you use R squared, which is a likely candidate for model specification issues, there are a number of points that you should be careful of. First of all, an increase in the R square, or even in the adjusted R square, does not mean that the added variable is actually significant. Okay? So even insignificant variables might increase the adjusted R square, and the unadjusted R square will increase no matter which variable you will add, even if they are ridiculous, because as we've seen last week, the R square will never decrease if you add another variable to your model. Okay? But even the adjusted R square might increase if you add an insignificant variable. Okay? Second, if your R square is high, or the adjusted R square is high, that does not mean that there's actually a causal relationship between your regressors and the endogenous variable. Okay? So causal relationships are the relationships we are interested in this course, but the R square can be quite low, even though there's a causal relationship, or it can be quite high, even though there's no causal relationship. Okay? So the R square does not signify whether or not there's a causal relationship between the regressors in your model and the endogenous variable. Also, if R square is high, or the adjusted R square is high, that does not mean that all the relevant variables are already included in the model. So omitted variable bias might be a problem, even though R square is high. And also, a high R square or a high adjusted R square does not mean that the model specification is correct, so that the regressors that are included in the model are the ones that should be included in the model. Okay? So be careful if you look at R square. There are a number of ideas which seem to be quite appealing, but which are wrong. Okay? And these are the 4 important points to remember if you deal with R squared or adjusted R squared. All right, so if R squared is not a good approach to model specification, how should we do that? And there's actually a kind of standard approach to model specification. And the standard approach is you start with a relatively simple basis model. For instance, the basis model which only a single regressor. And then you specify a number of plausible alternative models with additional regressors, and you estimate all of these models. And then you look at the coefficients you're interested in and check whether they do change in a marked way. Okay? So if they do, then it gives you important hints which models are to be preferred. Also, you should look at the question if the variables that you add to the model are really statistically significant. If not, it might be a better idea just to leave them out. But the most important rule here is that use your head and use your economic theory. Don't just follow strict rules. In this course, we sometimes do that. But if you do a real application, then do not follow strict rules. Think about the problem and think about the substantial issues that are at the basis of your economic question. So that's the most important part. After all, you are not statisticians, you are economists. And therefore, if you do econometrics, don't forget the economic theory. That's really important. All right, let's try to work a little bit on model specification for our running example. So which variables should be included in the California data set? And these variables could be grouped into certain groups, for instance, into school characteristics. So the school characteristics are those variables that could be influenced by policymakers, class size, the quality of the teachers, they could be trained better, the number of computers per student, the quality of the curricula, the expenditure per student, and so on. And then in the second group are the variables that relate to the students themselves. For instance, English as a native language, what's the percentage of English learners? This is outside the scope of policymaking. Are there any extracurricular learning facilities? This very often is also outside the scope of educational policy. What's the environment at home for the students? This is definitely outside the scope of policy. And what's the education of the parents? That's also just given. Okay. So that's already a first idea to group the variables into certain groups. And then we look at the data, which variables are actually available. And in the California data set, we have the class size, student-teacher ratio. We have, for instance, the share of non-native speakers, percentage of English learners. There are other variables. If you look at the data set, for instance, the share of students which receive lunch subsidies or social benefits, or the average income in a district. And we might then look at scatter plots of these variables and the test score, and we can see that there's a strong relationship if we have the percentage of English learners, if we have the percentage of reduced price lunch receivers, or the percentage of students from families that are qualified for income assistance. And then we set up different models. And the last part I'd like to talk about today is the presentation, the communication of your test results. Because if there's more than one model, the equations that you've learned about before are not easy to read. So in that case, it's better to build a table of estimation results. And rather than going through these points, we just have a look at one of these tables because they are almost self-explanatory. So what we need is the endogenous variable on top. Then we have, in this case, 5 different models. Here we have the list of potential regressors, class size, percentage of English learners, and so on, and the intercept. And in here, in this field, we have the point estimates and the standard errors. So, and we have blank fields for those variables that are left out for that particular model. So the first model only has a single regressor and an intercept. The second model has the class size and the percentage of English learners and the intercept. And then we have 3 more models. In this one here, we add the subsidized lunch. Here, we add the income assistance variable, and here both. And then we compare the outcomes. In addition, we have some summary statistics down here, the standard error of regression and the adjusted R-squared. And if you check that, you will see that the regressor, if we go from model 1 to model 2, goes down a lot, and then, well, varies a little bit. If we add to the second variable, the third one, then the coefficient changes a lot, and also it changes a lot if we swap the third for the fourth variable here. So if you compare these outcomes all together, then in the end, you will probably say that the best model to estimate is number 3. Okay, so it's the highest adjusted R-square, the lowest standard error of regression. This one is the same, but it has one more variable, which is not significant. So the best model is probably model number 3. But again, this is not really science, it's kind of art. So you really have to argue why that's the case. We are running out of time now, and that's in a way that's outside of what we are doing in this course. Here you are learning the technical part of this analysis, and the substantial part of arguing why a model is correct or not really depends on the question you're interested in. All right, are there any burning questions at the moment? Seems not to be the case. Then thanks for coming, and we are looking forward to seeing you, not next week, I think, but in 2 weeks. All right, thanks very much, and bye-bye.
Bye. Bye.